Hello and welcome back to Summer Work Help for Calculus 1. In this video we're going to be taking a look at question number 11. Now question 11 deals with radicals, which we also saw in question 3 and we will also see in the next question, question 12 and 13. So let's just dive right into it. So question number 11 just says simplify, and let's get to it. So for 11a, we have root 50. Now, as a side note, when you see a root and there is no number here, okay, when there's no number in the top left, there is an invisible 2. All right, so every single time you've seen a square root in your life, there has been a 2 in the upper left-hand corner. However, square roots are by far the most common roots. So just to make things a little bit simpler, for a square root, we don't write the 2, but it is there. All right. So I want to simplify the square root of 50. Now, when you're simplifying square roots, what you want to do is you want to think about the square numbers. Okay, so you can generate a list pretty quickly of the square numbers, because a square number, well, first of all, technically 1 is a square number because 1 squared is 1. Although for simplifying square roots, you can safely ignore the 1. All right. The next square number is 4. Right. So these are the square numbers on the right. Okay. Then 9, then 16, 25, 36, 49, and so on, right? So when you're simplifying square roots, you want to think about the square numbers, all right, but not 1, right? 1 doesn't really help you, all right? And the question becomes, what is the largest square number that goes into 50, right? What is the largest square number that is a factor of 50? So I can divide it evenly into 50, and the result is an integer. That's what it means to go into a number, right? So you can either start at the bottom and work your way up, or you can start at kind of a high number and work your way down. I tend to just sort of start at the bottom and work my way up. So 4 does not go into 50, so that's not going to work. 9 does not go into 50, so that's not going to work. 16 does not go into 50, so that's not going to work. However, 25 does. 25 does go into 50 evenly, because 50 divided by 25 is 2. All right. And then if you keep going, 36, 49, 64, 81, right? None of those square numbers are going to go into 50. So the largest square number, and actually the only square number other than 1, but the largest square number that goes into 50 is 25. So what you want to do is you can think of 50 as 25 times 2, right? You sort of break it up like that, right? And then you can break up the square root into 2 separate square roots like that. So now I have 2 smaller square roots, and the whole reason for doing this is that the square root of a square number should be an integer, right? So the square root of 25 is 5. And then the root 2, well, there's not a whole lot you can do about that. Root 2, it's irrational, but you also can't simplify it. So it's kind of stuck underneath the square root. So my final answer for number 1 is 5 root 2. B. B is similar to A, except it's kind of a larger number, and I've got some unknowns. So my first step, however, is not going to change. My first step is to ask, all right, what is the largest square number that goes into 128? And if you have a calculator, well, you should have a calculator. A calculator may help you here if you struggle to do this in your head. 4 does go into 128. Okay, so 4 is a square number that goes into 128, but you should keep going just to see, is there a larger square number that goes into 128? 9 does not go into 128. 16 does go into 128. So 16 would be a better square number to use than 4, because even though 4 is a square number and it goes into 128, it's not the largest square number. So far 16 is our quote winner, right? But let's keep going. 25 does not go into 128. 36 does not go into 128. 49 does not go into 128. But 64 does go into 128, and 64 is 8 squared, right? So 64 is a square number, and it goes into 128. And you can keep going, right? You can check 81, you can check 100, you can check 121, but none of the larger square numbers are going to go evenly into 128. So 64 is the largest square number that goes into 128. So I'm going to write 64. And 128 is 64 times 2. All right, so we're going to leave that 2 there. All right, now for the unknowns, for the variables here, I've got x to the 9th. Now with a square root, what I want to do is I want to try to ask myself, how can I group these x's so that they are a square number? Okay, so what I mean by that is I want to write this as x to the something squared, all right? And I want to get as many of the x's into this cluster as I can, right? So I have x to the 9th, all right? And I know that like x to the 8th, right? That's an even number, right? So I know that I can write that as x to the something squared, right? And remember, when you have a power to a power, you're multiplying. So I know that I can write this as x to the 4th to the 2nd, right? So I'm trying to take as many of these 9 x's that I have, and I'm trying to group as many of them as I possibly can into a something squared, right? And the grouping there is I can do x to the 4th squared, okay? And that's 8 of my x's, all right? However, I still have, it's 9 x's, right? I have x to the 9th, not x to the 8th. So then I have another x that is not going to get pulled out in front of the square root, okay? So that single x there is going to stay there, all right? And then the cluster that's underneath the squared, this x to the 4th, that I'm going to be able to pull that out from underneath the square root. I'm going to do the same thing with the y's, all right? I want to express y, and I want to express it as y to the something squared, and I want to pull as many of the y's as I possibly can into this thing. Well, I have y to the 5th. So I know that y to the 4th, right, because it's even, I should be able to express y to the 4th as this. And again, power to a power, you multiply. So what I've got is I've got y to the 2nd to the 2nd, all right? And that's y to the 4th. But I don't have y to the 4th, I have y to the 5th. So again, just like with the x's, I have a single y that's going to kind of stay underneath the square root. All right, now, I'm going to try to pull as many of these things out from underneath the square root as I possibly can. The square root of 64 is 8. And notice I'm no longer underneath the square root, right? So that 8 is out in front of the square root now, all right? I can't do anything with the 2. The 2 is going to stay underneath the square root. Now I've got x to the 4th squared. When I pull that out from underneath the square root, the squared is going to go away because the square root and the squared essentially cancel. And then I've got x to the 4th. And again, notice that that x to the 4th, that is no longer underneath the square root. It's just x to the 4th, all right? And I dropped the squared when I pulled it out from underneath the square root. The single x has to stay, okay? Then I've got y squared squared. When I pull that out from underneath the square root, the top squared cancels, and I'm left with just y squared. Again, I'm outside the square root. And then the single y has to stay. Now, everything that I was not able to pull out from underneath the square root is going to stay there. So the 2 is still there. the single x is still there, and the single y is still there. And so my final answer here is 8x to the fourth y squared root 2xy. And that is simplified. All right. There are other ways of sort of thinking about this or talking about it or teaching it or doing it, whatever. If you have another way of thinking about this that gets you to this final answer, then go with it, right? So, you know, the way I explained it is just one possible way of thinking about it. If you have another way of going about this that makes more sense to you and works and gets you this same final answer, then go with it, all right? There's other ways of thinking about this, but that's kind of how I approach these kinds of problems. All right, C. C is probably the hardest part of question 11, so let's just kind of dive right into it. So on the one hand, C is kind of similar to B in that we've got a root and we've got a coefficient, we've got x's and y's and z's and whatever, so it's kind of similar, right? The big change with C is that we are no longer dealing with a square root, all right? We are dealing with a cube root, all right? That's important. So in A and B, we were thinking in terms of like square numbers, and we were trying to like square things, all right? For C, we're going to want to shift our mind and to now think about cubes, right? So cubic numbers, and we're going to try to write things as to the power of 3, okay, instead of 2. But other than that, we're kind of do the same thing. All right, so C is a little bit different, but it's just cubed now instead of squared. So, I want to think in terms of, all right, what is the largest cubic number that goes into 375? All right, well, 1 is a cubic number because 1 cubed is 1, right? But 1 doesn't really help you because when you divide by 1, it doesn't change anything, right? So the cubic numbers are the ones that we care about, at least. Well, the kind of the first cubic number that we care about is 8, right? Because 2 cubed is 8. 8 does not go into 375, so that's not going to help. All right. The next cubic number, which is 3 cubed, is 27. 27 does not go into 375, so that doesn't help. 4 cubed is 64, which was also a square number, by the way, because it was 8 squared, right? But it's also 4 cubed, so it's also a cubic number. And 64 does not go into 375. 5 cubed is 125. And 125 does go into 375, right? So you can either write it as 5 cubed or 125. I'm just going to write it as 125. Oop, we'll use the same color here. If you write it as 5 cubed, that just kind of makes it even more obvious as to like what it's going to be. Because when we pull that 125 out from underneath the cube root, it's going to become a 5. But I'll just leave it as 125 for now. And then 375 divided by 125 is 3. So that's the factor that's kind of going to be left over underneath the cube root. All right, now I've got x to the 6th. What I want to do is I want to try to pull as many of those x's into a cluster that is something to the 3rd power, right? And the reason why it's to the 3rd power is because we're dealing with cube roots, all right? So I've got 6 of them, and I want to say, all right, how many can I possibly pull into this cluster of x to the something cubed, right? What is that something? Well, this one actually turns out kind of nicely because I know that if I have x squared, right, power to a power, you multiply, well, that's all of them. That is all of my x's, right? So I've basically just rewritten x to the 6th as x to the 2nd cubed, right? Because that is x to the 6th, because when you have a power to a power, you multiply your exponents. And I don't have any left over. I've used up all 6 of my x's. So I'm going to move on to the y's now. So same idea. I want to take as many of these y's as possible, and I want to cluster them into this group where I'm raising it, so y to the something, and then I raise that to the third power. Well, again, this works out actually quite nicely because I have 21 of them, and it turns out that if I have y to the 7th, okay, well, power to a power, 7 times 3 is 21. So again, by kind of clustering them this way, I've used up all 21 of my y's. I've clustered them into this y to the 7th to the third group, and I have none left over. Great. Same thing with the z's, right? I want to express z to the something to the third power. Right? I want to cram as many of my z's into this cluster as possible. So I have 17 of them, all right? And well, I know that 15 is it's a multiple of 3, right? 3 times 5 is 15. So if I do z to the 5th to the third, well, that's 15 of my 17 z's, right? And I can't do z to the 6th because z to the 6th is, well, 6 times 3 would be 18, and I don't have 18, I only have 17. So this is the maximum amount of z's that I can sort of cram into this cluster, and that takes care of 15 of them. But notice that I would still have two z's left over, right? So I need that z to the 2nd that's going to kind of be trapped underneath the cube root. All right, so now I'm going to start pulling stuff out from underneath the cube root. The cube root of 125, as we said, is 5, right? Because 5 cubed is 125. So when I pull that 125 out from underneath the cube root, I want the cube root of 125, which is 5. All right, the 3 is going to stay, so I'm going to pause on the 3 for a second. I've got x squared to the third power. Well, when I take the cube root of that, when I pull it out from underneath the cube root, the cubed and the cube root are going to cancel, leaving me with just x squared. And I'm out in front of the cube root now, because the cubed and the cube root canceled. Same thing with the y's. I'm going to take the cube root of y to the 7th cubed. So my cubes are going to cancel. My cube and my cube root are going to cancel, leaving me with just y to the 7th. And when I take the cube root of z to the 5th cubed, my cube root and my cube cancel, and I'm left with just z to the 5th. Z to the 5th. All right, I've got a couple things still left over in the cube root. I've got the 3 that was left over. I don't have any x's left over. I don't have any y's left over. And I've got the 2 z's that we weren't able to get out either. And so that is my final answer. 5 x squared y to the 7th z to the 5th times the cube root of 3z squared. That is as simple as I can make that original expression. All right, 11D. So 11D is the square root of negative 36. All right. For D, I'm gonna go slow with D, and I'm gonna write some stuff that you probably don't have to write down, but I just want people to understand what's happening here. So I've got the square root of a negative number, and technically, and again, you don't have to write out all of these steps, but to understand what's happening here, recognize that negative 36 is 36 times negative 1. Right? I think everyone knows that. Everyone knows that negative 36 can be rewritten, if you wanted to, as the square root of 36 times negative 1. And the reason why I'm writing that is because when you multiply, you can break up the square root. Now, if you're adding or subtracting, you can't break up the square root, okay? So if this was like 36 plus negative 1 or 36 minus negative 1, you can't break that up. But if it's times, right, you can break it up into 2 smaller square roots, like this. All right. Well, the square root of 36 is 6. And then what I have is I have the square root of negative 1. The square root of negative 1, by definition, is the imaginary unit. It's I. All right, and this is like hardwired into mathematics. All right, this is the definition of I. So I is defined as the square root of -1, which is exactly what I have here, right? I have the square root of -1. So when I simplify that, I get I, which is defined as the square root of -1. And that's as simple as I can make that. So I have an imaginary number. I have 6I. And if you have me in class, I'll say this in class. It's unfortunate that they're called imaginary numbers because they're not any more real or imaginary than like the quote real numbers, but the name has stuck, and so we're stuck with it. All right. So even though they're called imaginary, don't treat them any differently than you would other numbers because they're just as valid. That we just happen to call them imaginary numbers. And I'll get off my soapbox now. All right. E. So for E, very similar to D, I've got the square root of -192. So again, this first step is not strictly necessary, right? And the second step is not strictly necessary. You could just kind of jump right to just talking about I. But I'm going to write it out anyway. So for E, we've got the square root of 192. So what I want to do is I want to actually, you know what I can do? I guess I can do it in this step. I want to ask myself, all right, what is the largest square number that goes evenly into 192? All right, and you can just run through the list. 4 does, 9 does not, 16 does, 25 does not, 36 does not, 49 does not, but 64 does. And then any square number larger than 64, 81, 100, 121, 144, 169, 196, et cetera, et cetera, et cetera. None of them are going to go evenly into 192. All right. So the 192, you can think of it as 64 times 3. Okay. And that's just breaking down the 192 into a square number and then something else. All right. So now I can simplify this. The square root of 64 is 8. The root 3, there's nothing we can do about that, all right? So the root 3 kind of has to stay underneath the square root. And then again, by definition, the square root of -1 is the imaginary unit, which is I. So we end up getting 8 root 3 I. Now, this step right here, I would say is optional. And honestly, writing out this step is also kind of optional. So like if you can go directly from here to here, I would say that that's probably fine-ish. But you might want to check with your teacher to make sure that that's okay. But final answer, 8 root 3 I. All right, F. So F is a cube root. So I have the cube root of -8. And some students, especially, it's almost like students that have actually feel pretty comfortable with imaginary numbers and have worked with imaginary numbers before, might actually make kind of an interesting mistake. And they might look at F and they might say, oh, this is an imaginary number, because they're so used to seeing like, oh, a negative underneath a root means imaginary number. And that's not necessarily true, okay? If your root is an even root, right? So if it's a square root or a quartic root or a 6th root or an 8th root or a 10th root, then yes, that is correct. If you have a negative number underneath an even root, those are always imaginary numbers, okay? However, with an odd root, right? So a cube root, a quintic root, a 7th root, a 9th root, whatever, it actually turns out that a negative number underneath an odd root does not result in an imaginary number. And here's why. I want the cube root of -8. So just like with a square root, you want to think in terms of squared. Well, with a cube root, you want to think in terms of cubes. So you could say to yourself, all right, what's a number that when I cube that number, I get -8? And I would pause the video for a second if you don't know the answer to that. What is a number that when you cube it, right, what times itself times itself gives you -8? Pause the video, and hopefully you got -2. -2 times -2 is 4, times -2 is -8, all right? So when I simplify this, the cubed and the cube root cancel, and I'm left with just -2. That's my final answer. So the cube root of -8 is -2. Not 2i, not -2i, just straight up normal -2. Okay. G. G, I'm going to do a little bit quicker than the ones I've done so far, because if I take it kind of like methodically the way I've been doing it, it's going to take a while. So I would make sure that you understand the ones before G before you understand G, because I'm gonna go a little bit faster because I'm just trying to wrap this up a little bit. So for G, I want to simplify all of these square roots as much as I possibly can. All right. So -8 stays there. Square root of 32. Well, the largest square number that goes evenly into 32 is 16. Okay, no square number above 16 is going to go evenly into 32. And the square root of 16 is 4. So when I simplify it, when I simplify the square root of 16, I get a 4, all right? And 32 can be written as 16 times 2. So that 2, we weren't able to get rid of it. We weren't able to pull that out from underneath the square root. So the square root of 32 simplifies to 4 root 2. And like I said, I did that a lot faster than I did the earlier ones. So if you don't know how I got that, I would go back and check maybe like A or B, because that's how we simplify square roots. All right. Plus 5. I've got the square root of 18. The largest square number that goes evenly into 18 is 9, right? And 9 is 3 squared, so it's a square number, all right? So 18 can be rewritten as 9 times 2, and when I take the square root of 9, I get 3. And then 18, like I said, is 9 times 2, and so that 2 we weren't able to pull out from underneath the square root, so it stays there. Okay, plus 2. Then we have root 180, square root of 180. And the largest square number that goes evenly into 180 is 36. You're welcome to verify that, all right? And 180, I'll write this out. 180 is 36 times 5. So when I take the square root of that, the square root of 36 is 6, and then I'm left with that root 5 has to stay there. Okay, so I'm going to clean up each term. I've got 3 terms here. I'm going to clean up each one. So I've got -8 times 4, that's -32 root 2, plus 5 times 3 is 15 root 2. And then 2 times 6 is 12, and then a root 5. And I'm almost done. If you don't see what we're about to do, I would maybe pause the video for a second and see if you think you know what it is that we're about to do to finish up this problem. Okay. Now, the different roots here, you can almost treat them as like letters, as like variables, like x and y, right? So like if I had -32, I'll do this up here. If I had -32x plus 15x plus 12y, I'm pretty sure that just about everyone watching this video probably knows that you can combine the first 2 terms, right? You can combine the -32x and the 15x, and you get -17x. Well, with the roots, it's the same thing. If you have 2 roots that are identical, like root 2 and root 2, you can combine those. So -32 root 2 plus 15 root 2, just add your coefficients. So I've got -32 plus 15. If you want to do that on calculator, feel free. You get -17 root 2. just like we would have gotten negative 17x if we were talking about x. Now, root 5 is not root 2. Those are two different numbers, okay? So I can't combine those. So the 12, it's almost like 12y, okay? But I have 12 root 5, and then that is as simple as I can make that expression. So negative 17 root 2 plus 12 root 5. H. So h is the square root of 9/4 plus the square root of 36/25. Okay. Hopefully at least one of you has noticed that we're dealing with square roots here, and actually all four numbers here are square numbers, right? 9 is a square number, 4 is a square number, 36 is a square number, 25 is a square number, and just like you can break up a square root with multiplication, you can also break up a square root with division, right? So this first step, you don't actually need to write it out, but I'm just going to show you that because you're dividing, you can break up these square roots, right? You're allowed to do that, right? Square root of 9 is 3, square root of 4 is 2, square root of 36 is 6, and the square root of 25 is 5. So I have 3/2 plus 6/5. Now, you could probably use a calculator here, although we haven't used a calculator in this entire problem, or I haven't used a calculator yet in this entire problem, so I'm gonna keep it clean, I guess. To add fractions like this, you just got to get a common denominator, right, which is 10. So 3/2 can be rewritten as 15/10, and 6/5 can be rewritten as 12/10, right? So now I just have tenths, and 15 plus 12 is 27, and 27/10 is the same thing as 2.7. So I would say that either one of those answers would be fine. So either 27/10 or 2.7. I'll zoom back out. And those are all of my final answers for question number 11.